Welcome to qnawire.
In parts A, we want to figure out what the coefficient of static friction is and what the coefficient of kinetic friction is. This is the general force diagram for the problem. We have an applied force to the right, gravity down, normal force up, and a friction force opposing the motion to the right, so it's moving to the left. So if we just apply Newton's second law in the y direction, it's equal to 0 since it's not moving in the y. And this immediately implies that the normal force is mass times g. This means that the friction force is equal to mu s. In this case, it's not moving yet, so we're going to use mu s, not mu k, times n. And then when we add that in, we get mu s mg. So we're going to set that aside for now. So if we use that the applied force is 313 newtons, we're going to use the limiting force for the friction force here. We know that mu s doesn't have to take on its maximum value, but in this case, we're going to use the limiting applied force to get it moving. So we're going to use the limiting form for the static friction here. And so this could be a less than or equal to, but we're going to set it equal to like this. Now, sum of the forces in the x direction is equal to 0, since it's not moving yet, it has 0 acceleration. This implies that the applied force is equal to the friction force. Well, this is the friction force, and we know what the applied force is. It's 313. We know m and we know g, so we can solve for mu s, and we get mu s is equal to 0.71. That's one of the answers. Now it starts moving, and the force diagram looks like this, except for the friction force is not mu sn, it's mu kn. Okay. So if we do sum of the forces in the x direction is equal to 0, even though the box is moving now, it still has 0 acceleration. So we set this equal to 0. This yields the applied force is equal to the friction force again, and we're given a different applied force, but we solve for it the same way. We just get the coefficient, pin's glitching, coefficient of kinetic friction, pin's still glitching, is equal to 0.47. Now for part B, we want to figure out what we need to push in order to get the acceleration of 1.1 meters per second squared. And so we're going to use mu k, since the box is moving, not mu s. And we're going to use the same force diagram. We're just going to do Newton's second law in the x direction again. This case, we don't set it equal to 0 because we have an acceleration, so we set it equal to mass times acceleration. Sum of the forces in the x is the applied force minus the friction force. And we can solve this for the applied force needed. I'm plugging in that the friction force here is equal to mu k mg, since mg is still n. And so I get acceleration in the x plus mu kg, like that. And now I can plug in the acceleration here. I can plug in what we found in part A for here. We know what g is and we know what m is. And so the applied force to get this to happen is 51 point, or sorry, that's a different part. It is 256.77 newtons. Now in part C, we go to the moon, and we want to do some of the same analysis, except for a different gravitational constant this time. And so our force diagram, just going to draw it again, it looks pretty much the same, right? Applied force to the right, normal force here, mg down, except g is different now that we're on the moon. And we have a friction force. In this case, it's going to be static because we're not moving. In bullet point 1, we want to figure out what force causes it to move, but it's not moving yet, so we're going to use the static friction force here. So same thing, we're just going to do Newton's second law in the x direction. It's equal to 0 since it's not moving. And when we write this out, we get applied force is equal to static friction force, which is equal to mu s mg. In this case, we have to take care when we plug in for g. It's not 9.8 anymore. It's what it is on the moon. And so when we plug all that in, we get the applied force is 51.76 newtons. And then one more thing to do, bullet point 2. This wants the acceleration when we use the same force in part B. And so the force in part B was 256.77 newtons. And so here we're just going to use the same form that we found in part A. The applied force is equal to the mass times the acceleration in the x plus mu k times g. We're using mu k now because we're moving now. We can solve this for ax. And remember, we're not plugging in 9.8 for g because we're still on the moon in this part. When we plug in all these knowns, we get that ax is equal to 1.9 meters per second squared. So it's moving a little faster this time around because gravity's a little weaker. And that's the final